In this section, we're going to focus on POP packet structure. I'm going to open up a trace file called pop-normal.pcap, and this is a standard POP session where someone is opening up their mailbox and there's one message available and they're reading their mail. We can see the handshake process occurs, and POP traffic sits right after the TCP header. The default POP port will be port number 110, so we'll always see a port 110 in the POP traffic unless we're using a non-standard port. Once the connection is established, we can see the POP server responds, and these are the response lines from the server. The server will send back a response saying OK or something else right in this first byte position. In the filtering section, you'll be building a filter looking for all the OK responses. Here we have the user sending out a POP request, and this is one of the user commands. USER. This is when they put in their user name. They also use a pass command. And again, these things sit directly after the TCP header. So if I bring up the bytes view, we can see here's the TCP header, ends at offset 3.5 in hex, and the POP section starts at offset 3.6 in hex. Once the user finds that there's mail, then they begin the process of downloading this mail. And as we scroll through, all of a sudden we will see the retrieve command from the user, and here the mail begins streaming down from the server. When we look at the mail packets, we again see the plus OK from the server, and then the response description tells us how long that mail is and what the return path is, and this is the mail coming down to the end user. We can see that this piece of mail can't make it in this one packet, so there's a POP continuation packet. In that packet we have 1460 bytes of data after the TCP header, and that's typical that as you download all of your mail, you'll begin to see that these email messages won't fit in a single packet. They have to span multiple packets. One way of reassembling your mail so that you can view it easily would be to right mouse click and follow the TCP stream, and it will put together all of the command information as well as all of the data information, because POP always uses the same port number for both commands and for data, unlike FTP that uses different port numbers for each. In the next section, we'll go through building filters for POP traffic and filtering on specific POP command lines. Now we'll look at building a capture filter first, and then we'll go over to POP display filters, and then finally we'll go in and build filters based on specific fields in POP traffic. I'll open up the capture options window, and you can see that I already have a filter defined in there, so I want to get rid of that. And I want to check the existing capture filters to see if I have one pre-built for POP traffic, and I don't. So I'm going to have to build one. I'll call it POP3, and again, POP3 traffic runs over port 110, so I'll type in TCP port 110. If I want to save that filter, I'll make sure I click New, and now it's saved up in the filter window. I'll say OK, it's automatically applied that filter, and now if I want to start capturing some of that traffic, I'll just click Start, and it'll automatically capture the POP traffic. Now I'm going to open up an existing trace file and show you how to build a display filter, not just for POP traffic, but also for specific POP traffic based on the commands. I'm going to open up a trace file called pop and SMTP. There it is. And then here you can see we have some messenger traffic and we have some POP traffic. And we have some DNS traffic. We have all sorts of traffic. The easiest thing to do is just type in POP up in the filter window, and it will pull out all the POP traffic for you. In addition, if you want to, you could build a filter looking for specific commands in the traffic. Remember that as you work with Wireshark and you highlight a line inside of a protocol or an application, The bottom left-hand corner, Wireshark will tell you what the display filter syntax would be if there's one available. So there is one. It's called pop.request.command. So I'm going to right mouse click and prepare a filter based on this value. And we can see it pulled up the user command. So pop.request.command == user. Once I know that, I can hit Control-C and copy that and add to that filter. Now these commands are case sensitive. So if you put in user in lowercase, it wouldn't work. And now I'll apply that filter. And as you can see, I came up with 4 packets that matched my filter. There are the user commands and there are the pass commands. And that's it. Remember that if you like one of the filters you build, don't forget to click the filter button and type in a name. So this is pop, user, or pass. I'll click new, and now I have a new display filter that will check for the user or pass command in pop traffic. Normal POP communications are pretty simple. I'm going to open up a trace file called pop-normal. And we can see at the beginning that we have the handshake process. So POP always goes on top of TCP, so that's what we should see. The server comes back with a message saying OK. Now, I want to give you the list of the commands, the client commands, and the server responses. So we're going to go out to the RFC to get that information. The RFC provides you with the possible responses from a server as well as the possible commands from the client. And the sections that we're interested in are sections number 3, basic operation, and then also the transaction state and the POP commands section. So I'm going to go to section number 3, because in section number 3 you'll see what the server can respond with. And there are only 2 status indicators that will come from the server. There's either the plus OK or the minus ERR. So the OK is a positive response and the ERR is a negative response. They always will go in uppercase. So if you're going to build any sort of a filter on either the OK or the ERR, make sure that your filter is looking for the traffic in uppercase. Now I'll take a look at the command section, the listing of all the commands that the client can send on the cabling system. Here's the command summary. It's section 9, minimal POP commands. We can see user, pass, quit, stat, list, retrieve, delete, no operation, reset, and quit. Those are the basic commands, and you'll see those commands in the trace file. Here we can see the user sending the user command and then the username. The server comes back with a positive response saying, great, now I need your password, please. The client sends the password, and at this point the server sends a positive response saying that the mailbox is open and you have 1 message in the mailbox. Now the client asks for the status. And when the server comes back and gives the status, the server is actually giving the length of that email message in bytes. Now the client asks for the unique identification listing for that message. And the server provides the ID number that it's assigned to message number 1. This is the ID number that the server assigned. Now the client says, OK, list all of the messages, please. And the server does a scan and lists all of the messages that are listed. It will provide the message number and then the size of the message in bytes. These /r/ns there are carriage return line feeds. At this point, if the client is ready to pick up the message, it will send an RETR command, a retrieve command. Some of these commands, as you can see, are overlapping with the FTP command set. When the client says retrieve the message, the server says, OK, here's what I have. I have a message that's this many octets long, and it begins to send the message down to the client. Now we can see the message coming down to the client, and we can see that it didn't all fit into 1 packet, so it had to be continued. This email message is continued in packet number 17, and we can see the data down below. Client sends an acknowledgement for that, and we have a continuation. There's more information in that email message. Now, HTML messages are much longer than text messages. This one happens to be an HTML formatted message where the sender had their email address information at the bottom and their contact information in this blue font. And here we can see all of the settings for that. So it makes the message much longer. This is a really, really short message, but look how many packets it takes to get that message across the wire when they're using HTML. If you want to see the whole entire message, you can right mouse click and follow the TCP stream. The window will come up. You'll be able to see all the commands that went back and forth, and then you'll be able to read the entire email message. It's a very, very short message. It's a message that's been forwarded from one person to another person. We see the original message, and then we see the forwarded message right above it. I'll scroll down, and this is what takes up so many packets on the wire. All of this garbage, all the HTML stuff that's inside of HTML formatted email messages. I'm going to close this window down, clear my filter, and as we look at the end of the communications, you'll see that after receipt of the entire email message, the user sends a request to delete the file, this one file. The server responds and says, okay, that file has been deleted. At this point, if the user wishes to quit, they may, or they may come back and ask if there are any messages at this point. So there's the quit command, and there's the response from the server with its little sayonara saying goodbye. So it's pretty simple. In the next section, I'm going to show you 3 different trace files from POP communications that have something unusual in them or a problem in their communications. The first trace file I'm going to bring up is called POP3 problem. In this trace file, we can easily see why a user can't access their email. We see the handshake process takes place, and there's already a problem in the handshake process. If you notice, the very first packet there goes from the client to the POP server. It's a SYN packet. There's no answer coming back from the POP server, so the client waits 2.9 seconds for a reply. Finally, the client gets the SYN-ACK packet, and the client finishes up the 3-way handshake with an ACK. So already things don't look good. Could be that we have really, really high latency at this point in the trace. We really don't know why we have such a big delay. It could be really high latency, or it could be because the POP server is extremely busy. As we move further into the trace, though, we can tell exactly what's happening. We get a response from the POP server saying error. Now there's that -err, error, server too busy. Please try again in a few minutes. Now with a lot of email programs, they won't tell you that that's the problem. It just will appear like it's taking forever to pick up your email. It just sort of hangs in this state of, I'm trying to download, but it's really not trying to download your email. So looking at the trace when something like that happens can tell you right away what's going on in the background. In addition, we can look at that ERR line and we can right mouse click and apply a filter based on the selected value. And this is what it looks like to find a POP response indicator that's a negative. Remember, there are only 2 types of response indicators for POP. There's a -ERR or there's a +OK. I'll clear that filter out. We can see that the server says it's too busy, but the client has already gone ahead and sent its request across for its username, its address. At this point, the server begins to tell the client, I'm sorry, I want to shut down this connection. The client says, okay, and they finish this connection while the user goes through the process of doing a retransmission because it never got an acknowledgement for this line where it submitted its username. We can see that the email server explicitly resets the connection at this point. Now the client's got to go through the whole entire handshake process again to make a brand new connection to that server. Nothing will work until a brand new connection is established to that server. The next trace file I'm going to open up is called POP3 Problems 2. And this is typical. When people complain about email problems, this is typically what you will find. If we look at this communication, and I'm going to get rid of the packet window. We don't need to see that. We're trying to tell whether it's the email server that's got the problem or it's something else. There's that finger pointing where someone points and says the network is broken. Someone else says, no, 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 it's got to be the application. But the application people say they haven't changed the application. So looking at the packets can tell you the answer, can tell you where to point. Here we see a handshake process that occurs. Now in this handshake process, you're going to see something a little unusual because we have the SYN from the client to the server. We have the SYNAC that goes from the server back to the client, and our client turns around and sends an ACK packet. We see the server sending back a SYNAC again, and even though it's not listed as a retransmission, this is a retransmission of packet number 2. So it appears that the server may not have received the ACK packet just before it. We can see that there is a 6-second delay caused by that. My time display format is set to show me the seconds since the previous packet. Anytime I'm troubleshooting a problem with performance, I'll set the time display to show me the seconds from the end of one packet to the end of the next packet. And here we can see there's a 6-second delay just right there. Our client turns around and sends the ACK packet again. And now the server does believe that the handshake has completed successfully, so that ACK packet must have made it. So it sends a positive acknowledgement. Now, you don't need to pay attention to the fact that the TCP headers may have checksum faults, because I went through and edited some of these packets to get rid of usernames. Now our client sends the user command with their username, and the email server doesn't respond, so we go through the TCP backoff algorithm, and the client tries again about 3 seconds later, and then the client doubles that to about 6 seconds later, and then the client doubles that to about 12 seconds later. Finally, we get an ACK from the server saying, I received your user command, and your username is accepted. Now the client sends the pass. Look at the amount of time that it took for that fault right there. Unbelievable. That's 18, 19, 20, 21 seconds that it took right there. At this point, the user is sitting and just wondering what is taking so long to pick up their email. There we can see the user. We've got another retransmission, so there's another 2.4 second delay. This is really, really terrible performance, and it seems that packets are being lost going to that server. There's the client requesting the unique identification listing for the email. The client gets that information down, and even through the process of going and just sending a quit, there are retransmissions. So this is horrible, and I'm going to change the time value to show me from the time that this trace started, how long did this whole thing take. So we start up here at 0 seconds, and we can see that just going in to check for the email, and there wasn't any email in there, it took 35.8 seconds. Imagine if the user had 5 or 6 emails that they had to try to download during that process. So is the POP protocol at fault here? No. It's packet loss. We have packet loss. What we would do is we would probably take the analyzer and go closer to the POP server and try to pick up the packets right at the POP server to validate that the POP server is not sending packets out at any point, and to try to narrow in on where the packet loss occurs on the network. The third trace I'm going to open up is called pop-spam clog. Now this is somebody trying to download their POP messages, download their email, and it just seems like it's taking forever. Now the reason why it's taking forever is because a majority of the traffic that's coming down to the user is spam. And in that spam that's coming down, there are attachments that are really large. So this company does not have it set up so that they can filter out attachments, although at the user system, the virus detection tool will filter out the attachments, but the user still has to wait for all this garbage to come down to their system. We can see the client saying retrieve message number 20. Now I want to build a filter looking for the retrieve command so I can see all of the times when they said they wanted to retrieve a packet. So I'm just going to filter on the retrieve command. Here we can see the filter syntax. pop.request.command is equal to retrieve. I'll apply that, and we can see that they're retrieving 20, 22, 24, 26, 28, 30, 32, 34, 36, and then 12, 13, 14, 15. Now at this point I want to see what is coming down to the client, so I'll clear out my filter, and I'm simply going to right mouse click on any one of those pop packets cruising along. Here we go, there's a pop packet. In fact, to make this easier, let's place our pop filter on here. Get rid of everything else. I'll right mouse click and say that I want to follow the stream. Now there we can see the first retrieve command. We can see the information, and guess what? It's me. Yeah, this was me logging into our server trying to get my email, and it took forever. And every time I experience a problem like that, I'll immediately grab the traffic, because now I have a great trace file that shows me what's going on in the background. And from looking at this, we knew, okay, we need to do some sort of cleanup at our email server. Here we can see there's the attachment that came with that one email, and it's just a piece of spam garbage that was coming in from some, I don't know, what is this, info@surfmotelfortbragg.com. So as I scroll down, you can see the length of this garbage email. I don't want that stuff coming down to my system, but because of the way we were set up, that's what we had to go through. That's just one email message right there. Now I'm getting into another email message. Now this one's different because it comes from somebody at bham.wednet.edu, or it appears to, and it appears like it may be the same spam attachment because, you know, they're kind of grouped together when those things happen on the internet. You get the spam folks out there and they send huge mass quantities of this garbage at the same time. Here's another one coming allegedly from somebody at freos.com, and it's the same thing. But look how awful that is. I'm just going to look and see how long this download process took. In the left-hand side, and I'm just filtering on the POP communications here, the time value, in order to measure this, the time value should be set to the seconds since the beginning of the packet capture. And we can see that we start at 0, and ouch, look at that. No wonder I was irritable that day. Look how long it took just to get through the spam garbage. I hadn't even gotten onto my regular email yet. So that's a perfect case study that explains why we need to have some strong filtering at our email servers. Don't wait till the spam garbage reaches all the way down to the client system.